annoying thing here that needs to be removed.
Okay, so hopefully everyone can see this. If you can't, please shout out. Okay. I don't know. Maybe we can put it up like that, so they can somewhat see me. Okay, good. So yeah, so I say that I'm talking on point-free topology and constructive mathematics. So I think the first thing we can start with is the point-free topology part. But actually, I'm just going to talk about topology in general to start with. I assume everyone here knows topology, but maybe not from this perspective before. So maybe forget everything you know about topology for a bit. And we can just consider an example I have here. So suppose you're given some kind of physical object. So here I say some kind of like steel rod or something. And we want to talk about some properties of this object. So what can we say about, say, the length of this rod? And I want to know the things that I want to know, what can you say for certain? So what can you actually be very confident about the length of this rod? So as an example about something that we could not say is we could not tell that its length is exactly 10 centimeters. So suppose for now that its length is actually exactly 10 centimeters, but we cannot possibly ever tell this. Because if you wanted to go about trying to do it, you might say, okay, I'm going to get a ruler and I'm going to try and measure the rod. But whenever you measure it, there's going to be some kind of inaccuracy in your measurement. So here I say maybe we measure it to be 10.1 centimeters plus or minus 0.3. So this is consistent with the length being 10 centimeters. But we don't know that its length is exactly 10 centimeters. The length could be, say, 10.1 centimeters. So that's not something that we can tell. Because so now we could say we can get a more sensitive measurement, right? But we still can't tell. So no matter how sensitive you have your measurement, you will be consistent with it being 10 centimeters, but you can't, who knows, maybe it's 10.000005 centimeters or something, right? So you can't tell that it is exactly 10 centimeters long. Okay. But what can we say? Does anyone have any examples of something that we could definitely say? I have this rod, and what about its length? Can we say for certain? I mean, supposing that it actually is true. Yeah. Okay. So what kind of interval? Like, give an example. Okay, but I guess I'm asking what kind of interval? An open interval. Yeah, so yeah, we can. So here I'm, as in the example, I'm saying something similar to that, but I guess simpler. So we can say that its length is, say, strictly less than 10 centimeters. So if it was less than 10 centimeters, we would be able to tell that if, say, we did some measurements and we see that it's 9.91 plus or minus 0.02 centimeters. Okay, this will, then we know that within this, even though we have some error, we do know that it's strictly less than 10 centimeters. And it's always possible to find some sensitivity such that you can show this, because if the length is less than 10 centimeters, it's less by some epsilon, and then you just do a measurement that is precise, like up to, say, epsilon over 2, and then if you do a measurement that precise, you will be able to tell that it is strictly less than 10 centimeters. So this is something that we can tell, that it's less than 10 centimeters. We wouldn't be able to tell that it was less than or equal to 10 centimeters for the same problem we had before. If it was exactly 10 centimeters, then we wouldn't know. So this is related to this idea, or the fact that this interval is an open interval. So if it were a closed interval, it wouldn't work. But because it's an open interval, it's possible. So if we say that the space of all possible lengths of the rod is the positive real numbers, then we see that this is an open subset of this space. And in fact, the open subsets of the space are precisely the sets, such that if the length were in the set, then we could verify this by finite means. So these are precisely the things that we can tell with our kind of only finite precision measurements, as long as we can do arbitrary precision, right? The precision is finite but arbitrarily good, then we can tell that they are in this set. But if the length is not in the set, we can't say anything one way or the other, right? So if it's not in the set, we don't know, but if it is in the set, then we can tell. Okay, so open sets we can think of as being verifiable properties. So these are properties that when they hold, then you can check that they actually do hold. And you can say that this is what topology is the study of. Topology is the study of verifiable properties. And because these are kind of properties that something can have, they come with a logic where we can kind of manipulate these properties. And this logic of verifiable properties, it's called geometric logic. Okay, so they're going to satisfy certain properties, this logic. There's certain things we can do with these propositions. So the first thing to notice is that if you just have a property that's always true, then this is verifiable. And the idea is because it's always true, there's nothing to verify, right? It's always true, so you don't need to do anything to verify that it's true. Okay. On the other hand, if you have two verifiable properties, then their conjunction is verifiable. Because, okay, so how do we check something's verifiable? Well, we assume it's true, firstly. So U meet V is true. And that means in particular, U is true and V is true. So because U is true and it's verifiable, we can verify U. And then because V is true and it's verifiable, we can verify V. So now we verified U and we verified V, so this verifies U and V. Okay, so the conjunction of two verifiable properties is verifiable. Now, also, if we have an arbitrary set of verifiable properties, then their disjunction is verifiable. So how does this work? Well, in order to verify a disjunction, well, the disjunction is true. So if the disjunction is true, it must mean that one of the things in the disjunction is true. And then we can just verify that one, and that will verify the entire disjunction. Yes, right.
So we don't sort of account for the fact that it might take infinitely long to find the thing that's true.
Yeah, no, good question. So yeah, so all I'm saying is that you could verify it, right? You're honest, sure, this is some uncountable set or something. Then how do you know which one you need to verify? The point is that there exists some kind of way of verifying it. So that if you saw it, you would be convinced. We aren't necessarily saying anything about whether it's possible to find this verification by some kind of exhaustive search or something. But yeah, it's a good question. Notice as part of this, also the property that's always false is also verifiable. This is vacuously true, right? Because you only need to verify things when they're true. So if it's always false, it's just vacuously verifiable. The other thing I want to point out is while we can take arbitrary joins or arbitrary disjunctions, we can only take finite conjunctions because if you had an infinite conjunction, you would need to, in theory, check infinitely many things, right? We're only allowed to do this by finite means. So if we have two verifiable properties, we can verify each of them in turn. But if we had infinitely many, we can't verify all the infinitely many things. So that's why we only have finite conjunctions. So now what we can do is if we have a set of things which might satisfy these properties, we can identify the verifiable properties with a set of things that satisfy them. So we just think of the properties as corresponding to their extensions, right? So just we identify them with the things that satisfy them. And then these conjunctions and disjunctions become intersections and unions. And these properties we've just seen for verifiable properties, these are precisely the axioms of a topological space. So this is why the axioms of a topological space are what they are. This is why, for example, you allow arbitrary joins, but only finite means. So I think this is why this is a very nice approach, because it really kind of, I think, gives a very good motivation for why the axioms of a topological space are what they are. But it doesn't only tell us about topological spaces. We could also talk about functions. So here I'm saying, suppose we have some kind of function which we could actually implement in the real world. So I'm not really thinking about this so much as some kind of mathematical function, a functional relation or anything. I'm saying this is more like, I guess, more like the computer science idea of a function, or some kind of function, some kind of procedure which we could actually carry out. So for example, with our rod, maybe we have two rods, and then you could like stick them together and ask the length of the kind of concatenation of the two rods, right? So this is some kind of like addition. So addition is something which we could carry out in the real world in this sense. So if we have such a function, you can now ask, can we verify whether something lies in the preimage of some u? So if u is some verifiable property in the codomain, we can ask, can we verify whether x is in the preimage of u? And to verify this, all we need to do is we need to take x, we need to apply this function, and check whether it's in u. So we can check whether it's in u because u is verifiable, and we can apply this function because this is a function we can actually compute in the real world. So this tells us that the preimage of an open set should be open, right? So whenever you have a function that you can actually implement in the real world, it should be continuous. So this gives us, again, a motivation for the idea of a continuous function. Okay. Are there any questions about that so far? Okay. I guess the other thing this tells you is that probably mathematical concepts will come maybe equipped with some kind of natural topology, right? And that all of the functions you want that should actually be able to be implemented should be continuous with respect to this topology. So that's maybe another thing that this kind of suggests, which is maybe not appreciated by that many people.
But the natural topology is the verifiable property.
Yeah, the ones that you could actually verify, right? At least if this is something which has any link to the real world in any way, you'd think that the natural topology is the things that you can actually verify, right? Okay.
Does it have to be unique?
Does it have to be?
Unique.
Well, yeah, I mean, yeah, there's, yes, so whatever concept you have, I mean, if there's some unique way that it can manifest in the real world, then there is a fact of the matter for what the things are that we can actually verify. So that would give a topology. Now, of course, sometimes you might say, actually, I want to restrict to a coarser topology by considering only things I can verify in a certain way or something like that. So, of course, things like that are possible. Like, it's possible you might want to like use other topologies for reasons such as that, or perhaps you have like a particular, like if you have a particular abstract set, of course, you can put different topologies on. But if we're thinking about it as being something in the real world, there will be one like natural topology, which is all the things that you can verify. Okay, so this is kind of how people do it in classical topology, where they identify these verifiable properties with the sets of things that satisfy them. But we could also study these verifiable properties in a more abstract way. So we don't say, oh, we're going to identify the properties with these things that satisfy them. We're going to say, I'm just going to consider these as propositions, and I'm just going to study them that way. And then if you kind of consider the set of all of these propositions, that will have certain structure, and that's what we're going to call a frame. Okay, so more formally, a frame is going to be a kind of poset. So you can think of this order structure as telling you when one proposition kind of implies another proposition, or when one is a stronger proposition than another, or you can think of it as just being this idea of kind of superset in the case of topology. And then we have finite meets and arbitrary joins. So the finite meets corresponding to our finite conjunctions, the arbitrary joins corresponding to our arbitrary disjunctions. And they satisfy this certain distributive law, which says that finite meets distribute over arbitrary joins. It's quite easy to see that this will always hold in the case of a topological space. So if we take the opens of a topological space, those will always form a frame. And you will always have this distributive law because it holds for sets, right? And it's also quite easy to see, or if you think about it a little bit, that for the logic to behave reasonably, you also want this distributive law to hold for the logic. I guess one thing to point out is I say we have arbitrary joins, and that means automatically that you get arbitrary meets, right? Because if you have arbitrary joins, you also have arbitrary meets. You can always prove that. But these arbitrary meets are kind of like second-class citizens. We kind of think this is almost an accident that you get these arbitrary meets. They maybe don't behave the way you think. So what do they give in the case of a topological space? What it is you take the intersection of the sets, and then you take the interior of that intersection. So it's kind of a bit of a strange property. We kind of don't view that as part of the structure. The things that we view as part of the structure are the finite meets and the arbitrary joins. And when you kind of think of these as operations on the set, you actually see that frames are certain kinds of algebraic structures. So you have these operations. You have an nullary operation, which gives you the top element, which we call 1. You have a binary operation, which takes the meet of 2 elements. And then for every kind of arity, you're going to have a join, or like for every cardinality, you're going to have a join of that arity. So you end up having a proper class of join operations, which might make you nervous, but it turns out that everything works fine, and you still get something which is monadic over set. So it behaves very much like any other kind of algebraic structure. Yeah. So the forgetful functor set, it has a left adjoint. This induces a monad on set, and the category of frames is the Eilenberg-Moore category for that monad. But really, it behaves like an algebraic structure. It's just like groups or anything like that. Okay, so because it's an algebraic structure, there's a notion of a frame homomorphism, right? And a frame homomorphism is just going to be a function which preserves all the operations. So in other words, preserves finite meets and preserves arbitrary joins. It doesn't need to preserve the arbitrary meets or anything like that. You can also kind of think of this kind of from a logical perspective. If we have this collection of verifiable properties and then another kind of collection of verifiable properties for something else, this is going to turn kind of a map the first kind of verifiable property into the second kind of verifiable property, and it's going to respect the kind of logical operations. Okay. But really the big example of these are continuous maps. So if you have a topological space, I told you that the open sets form a frame. And if you have a continuous map between topological spaces, you can take the preimage. So the preimage of an open set will be open. So this will give us a function from the open sets in the codomain to the open sets in the domain. And preimage preserves all these set theoretic operations, right? So in particular, it'll preserve the finite intersections and the arbitrary unions, which are our frame operations in this case. So a continuous map between topological spaces gives you a frame homomorphism, but notice the frame homomorphism goes backwards, right? So if your continuous functions from x to y, your frame homomorphism will be from the opens of y to the opens of x. Okay. So this will give us some kind of contravariant functor from topological spaces to frames.
Graham, I have a question.
Yes.
So you were saying that frames are monadic over set.
Yes.
Topological spaces are not. Can you give me any vision for which frames work, but topological spaces don't?
So I guess the one point that I am almost getting to now is that it would really be kind of the opposite of topological spaces rather than topological spaces, which would be the correct analog. Because as I just said, the morphisms in frames kind of go in the reverse direction to the morphisms of topological spaces. So it's more like the opposite of the category of topological spaces, which might be monadic over set. So is that clear that maybe it should be the opposite, or should I say something about that?
Yes, that's clear. Now I'm wondering if then I have a comonad for topological spaces or not, but
yeah, so I think for the opposite of the category of topological spaces, I think there are ways to kind of approximate, like firstly, I guess you need to ask what's your forgetful functor. So if your forgetful functor is just taking the underlying set of the topological space, that's not analogous to what we're doing here, because the elements of the frame correspond to open
Yes,
sets.
yes, that's right. Maybe this is the point then.
So the forgetful functor would need to go from the open sets. And then I think there's a way, if you do that, there's a way to kind of turn functors into monads and stuff, like approximate it. And I think you end up just getting frames if you actually work out what the algebras are in this case. But I'm not completely certain about this.
Yes, I see. Thank you very much.
Okay, sure. Okay. But as I was saying, so really it's the opposite of the category of topological spaces, which is like frames because of this reversal of the order. So if we want to think of frames as actually being like topological spaces, we actually want to reverse the order of the frame homomorphisms. So when we're thinking of frames as being spaces, we call them locales. A locale is just a frame. It's not different to a frame. It's exactly the same thing as a frame, but it's when we're thinking of the frame as being a space in some sense. And then we define a category of locales to be the opposite of the category of frames. So a locale morphism is a frame morphism going backwards. So this is because this makes this map, this functor between topological spaces and frames, which is contravariant. It gives us a covariant functor from topological spaces to locales. So really, if you kind of want to use your spatial intuition, or you want things to work in the same direction, like products to be comparable in, say, in the point-free setting and the point-set setting, you really want to be working with locales. But of course, when you actually want to do calculations, at the end of the day, you're going to use frame homomorphisms and things. But it's just a formal thing we do in order to make it act more like topological spaces. And then again, so we don't get confused about what directions maps are going and things, we're going to like maintain a notational distinction between frames and locales. So they're the same thing, but we're going to call the locale something like X. And then you're going to call the corresponding frame OX. That's like opens of X. So you're already thinking of the locale as being like a space. And then if you call the locale map F, we're going to say that F upper star is going to be like the frame homomorphism corresponding to F. So the upper star is supposed to remind you of this pre-image idea. Okay, does that make sense? Cool. So that's the idea of what a locale is. So when we had a topological space, we started with a set of points, and we had a frame of opens. When we have a frame, we just have a frame of opens. There's no set of points. But it turns out just because we were told, we weren't told what the points were to start with, doesn't mean we can't come up with a notion of points. So we aren't explicitly told what the points are that satisfy these properties. But we can think about what points actually give from a logical perspective. So from a logical perspective, what a point gives you is it gives you a model of this theory of verifiable properties determined by the frame. So if you have a point in a topological space, you can say, which open sets does the point lie in? And we're thinking of the open sets as being properties that the point would satisfy, right? So if you consider all of the properties that the point X satisfies, this is like a model of the theory of the verifiable properties, right? It tells you which properties are true. So we can still ask without having a predefined, so the set of points we had was like some kind of distinguished class of models or something we had for the topological space. But in this case, we can still ask what should a model be of this geometric theory. So as I say, the model is going to be a consistent assignment of truth values. So for every verifiable property, we're going to say, is it true? Is it false? And it must somehow be consistent with the kind of operations we can do. So in particular, this means that this top element must always hold, right? It's the thing that's always true. So it should always hold in our model. So that should be something which holds in the model. If A holds in the model, and A is less than or equal to B, then B should hold, right? Because B is a weaker condition than A. If A and B both hold, then A and B should hold, right? The conjunction of A and B should hold. And if you have a arbitrary disjunction, which holds in the model, then one of the disjuncts should hold. Okay, so these are the conditions you need for something to be a model, and this is what we call a point. So we define this to be the point of a frame. So yeah, so
This is essentially an
yeah, it's like, okay, so depending on how you define ultrafilter, like yeah, so it's not like a maximal filter or anything, but it's a prime. So an ultrafilter, it's equivalent to being a prime filter, right? So this is like the definition of a prime filter, but it's actually what's called a completely prime filter because we have arbitrary joins rather than just finite joins. But yeah, otherwise it's very close to the definition of an ultrafilter. Yeah, at least it's the analog of an ultrafilter in this setting. So yeah, so this is what we call a point of the frame. So from a frame, we can recover a notion of points. It's not a kind of thing that we start with, but it is something we can discuss. Okay. So now I want to say something a little bit, something about the relationship between locales and spaces. So we've seen how every topological space gives rise to a locale from its frame of open sets. And a continuous map will give you a frame homomorphism by taking the preimage. So in other words, it gives you a locale homomorphism in the same direction. And this gives a functor from topological spaces to locales. And this functor has a right adjoint. And you can maybe guess what the right adjoint should do. It's going to take the locale, and it's going to give you a topological space whose underlying set is the set of points that we just described. And I say equipped with the obvious topology. So I'm not going to go into the details, but the idea is for every element of the frame, that's going to give us, like the points correspond to these models. So you want to say which models satisfy this property. And that will give you a set of points. And this will be the open set corresponding to that element of the frame. And you can do this for every element, and you can end up getting a topology on the set of points. And this gives you the right adjoint, as I say. And this adjunction is what's called an idempotent adjunction. So it behaves maybe even better than a normal adjunction. An idempotent adjunction just means that if you start at, say, locales, and then you go to spaces, and then you go back, and then you go back to spaces, and then you go back again, it's the same as just going forwards and backwards once. It's not like you can keep on getting different things as you keep on going backwards and forwards in the adjunction. And so what we care about is the kind of two special classes. They're the locales that come from a space, and these are what we call spatial locales. And then they're the spaces that come from a locale, and we call these sober spaces. So this isn't an equivalence. So not every locale is spatial, and not every space is sober. But I guess what I kind of want to emphasize is this condition of being sober is quite a weak condition. It's not something which is very strong. Probably every space you care about is sober. This is probably true. On the other hand, in the constructive setting, spatial is a big restriction. So coming from a space is really not something we want to impose, at least in the constructive setting, which we'll see later, because like even the real numbers, constructively, you can't show that they're spatial. So if you care about the real numbers, you need to care about non-spatial locales. Okay. I guess the other thing I want to say about the fact that this isn't actually an equivalence is also saying something from a logical perspective. It's saying that we don't have a completeness theorem for geometric logic, or at least the completeness theorem for geometric logic doesn't behave in the way that you might naively expect it to. So you can have propositional theories that aren't completely determined by their models. So we will see some examples of that later. Yeah.
shows and stuff, I understand. If you start with the reals,
Yeah.
and then you get the open sense of the
Yeah.
reals, then you could have a sort of a filter that's homing in on an infinitesimal. Would that not extend to the kind of?
Yeah, so if you start with the reals with the usual topology, and then you get a frame,
Yeah.
and then you go back, you will get precisely the original points you started with. You won't get new things, because I guess it's because you're thinking of you're thinking of prime filters, but these are completely prime filters, which is like a very strong condition. So the only way you can satisfy it is by actually being a point of the reals, it turns out. So the reals are sober, in particular. So yeah, so you don't get anything new. And when I say the reals don't have to be spatial, though, I guess I'm using a different definition of reals. I'm using a point-free definition of reals, which in the classical setting gives you the usual space of reals, but in the point-free setting does not necessarily. But yeah, so I guess this, yeah, I think, I mean, of course you could do things in like a non-standard way and stuff, but I think, yeah, just the kind of straightforward way of defining what the points are, you're going to get the normal points back. Okay, good. Yes?
Just a quick question. These points, do they correspond to exactly frame homomorphisms into two?
Yeah, we're getting there. Well, no, into truth values, which classically is two. Yeah, okay, but we'll get there. Classically, it's into two. Yeah, but we will get there. Okay. So yeah, they correspond to maps from the terminal locale into the locale you care about. Okay, so the next thing is constructive mathematics. So that was the first half of the talk. Now the second half, and I have much less than half the time, but hopefully we'll see how far I go. Okay, so I think in order to understand constructive mathematics and not be very confused, it helps to first kind of talk about what do we mean by a logic. So what even is a logic? So I'm saying here classical logic that you're probably all familiar with is what that's talking about is maybe some Platonic notion of truth. So we're saying that we're really imagining they're actually going to be these things such as like real numbers or whatever else, whatever other mathematical objects. And we think of these as being real things. So of course, they should have definite properties. So for everything we ask, it should either be true or it should be false. And we kind of reason about it in this way that we're very familiar with. And if you have this kind of idea, constructive logic is maybe going to feel very strange sometimes. But I think the thing to think about is that logics can describe much more than just this idea of Platonic truth. There are other things that logics can talk about. So maybe what a logic will talk about is not some Platonic notion of truth, but maybe just what we already know to be true. So we maybe don't want to give truth values to things that we haven't yet found out to be true or something. And then you could see how this could kind of change things a little bit. Or maybe we want to use a logic to describe computability. So when we say that some proposition implies some other proposition, we don't just mean that if we say A implies B, we don't just mean B or not A, or which is what it would be classically equivalent to. We might say, no, I want to actually take some kind of computer program that I can run that takes some kind of solution to A and gives us a solution to B. So we might want to use a logic to talk about computability. Or we might want to talk about a notion of local truth. So maybe our propositions can actually vary by different, like according to where you are in a certain space. And the truth values will tell you where something is true. It might be true in some places, but not other places. Or what we've been speaking about for kind of this talk so far, verifiable truths, where you aren't talking about just kind of an arbitrary notion of truth, but you want everything to be verifiable. Or you could be talking about probabilities, or you could be talking about possibilities, or fuzzy concepts, or resources. All of these have logics. Okay. Now, the ones that I've highlighted in green, these are the ones that we care about for constructive logic. So I've highlighted this Platonic notion of truth. And this is because intuitionistic logic is a generalization of classical logic. So if we prove something constructively, it will also hold classically. So we do care about the usual Platonic notion of truth, but we also care about these other things. So this first one, what we know to be true, I'm trying to kind of gesture at this notion of intuitionism that the intuitionists kind of cared about. They were kind of caring about these things that you don't want to say like too much about the things that you haven't proved one way or the other yet. They only want to talk about things they've already proved. Okay, computability I spoke about, local truth I spoke about. So all of these are kind of like, you can think of these as being models of constructive logic. So if you want to understand kind of how something works in the constructive setting, just come back to these examples. Think, what would happen if I wanted everything to be computable? What would happen if I wanted to consider this idea of local truth? What would happen if I wanted to do the normal classical version of mathematics? And all of these are kind of good test cases to think about when you want to reason constructively. So I think these are always good examples to come back to. And I think let's look at one of them in more detail. So suppose we have some proposition, and the proposition depends on location. So an example could be, is the temperature greater than 0 degrees? Now, so it depends. Suppose we're on the Earth. So we know we're somewhere on the Earth. But this question will be true in certain places on the Earth and false in other places on the Earth, right? So it's not just a yes or no question. Yes, the temperature is greater than 0 degrees. No, the temperature is not greater than 0 degrees. We're going to have some region on the Earth where this is true. So let's suppose that this region is an open set in some topological space. Okay. So now our kind of truth values aren't going to be just true and false. They're going to be kind of a region on the Earth, an open set. And here, our usual notion of like the top, the truth, that means it's true everywhere. And the bottom, the falsehood, that's just going to be something that's true nowhere. And then when you take conjunction or disjunction, it'll be intersection or union of regions. But if you think about negation, things are going to get a little bit subtle here. Because if U is an arbitrary open set, its complement is not usually going to be open, right? So for the negation, we won't take the complement, we're going to take the interior of the complement. But if you have an open set that is not clopen, then this interior of the complement is going to make it smaller, right? It's going to be less than the full complement. So when you take U, union, the interior of the complement, this won't be the entire space. So this won't be true. It won't be the thing that's true everywhere. It'll only be true in some kind of dense subset of the entire space. So we say that the principle of excluded middle fails. So the principle of excluded middle says that if you have a proposition and you have its negation, one of them is true. So P or not P should hold. But here we see that in general, we don't have that P or not P holds here. So this is kind of the big thing which fails in constructive maths. In fact, we can say in intuitionistic logic, it's kind of like classical logic, but we remove the principle of excluded middle. And by that, I also mean we remove other equivalent statements like double negation elimination, which says that not P implies P. Now, okay, formally, this is not a formal definition, but this is also not a course on formal logic. I think this is maybe intuitively a good way to think about what intuitionistic logic is. One thing to point out, though, is when you have excluded middle, you can define implication in terms of not and or and stuff. But when you have constructive logic, you can't do that. So we need to add an implication as some kind of basic operation. And then we can define negation from that. So not P means P implies false. So when you have classical propositional logic, you can study it with the notion of a Boolean algebra. For intuitionistic logic, it's very similar, but instead you have this notion of a hating algebra. And here I have the definition. A hating algebra is just a lattice. and it has an operation which is essentially its right adjoint to your meet operation. So what you can, a hating algebra, I guess, for the category theorists, we can say that, so it's a thin category, so it's like a poset viewed as a category, and then it has finite limits and finite co-limits, and it has exponentials, right? So it's some kind of Cartesian closed category. Yeah. So this is the notion that we consider for intuitionistic logic. So of course, Boolean algebras are all hating algebras, but hating algebra is something more general. Okay. So if we're in a frame, you can take any element and you can say B meet blank. That's going to be a map from the frame to itself. And because of this distributivity law for frames, it'll preserve joins. So it's a map between complete posets that preserves joins. And so it does have an adjoint. It has a right adjoint. And so frames are hating algebras. On the other hand, frame homomorphisms don't need to preserve this operation. So this adjoint always exists, but it's not preserved. So it's another one of these second-class citizens, like arbitrary meets. It exists in frames, but it's not preserved by the homomorphisms. On the other hand, a general hating algebra doesn't need to have infinite joins. So a frame always has infinite joins, but an arbitrary hating algebra doesn't need to. So it seems like there's some kind of link between hating algebras and frames, but they aren't exactly the same thing. And one doesn't include the other. So what does this tell us about intuitionistic logic versus geometric logic? Also, I told you this idea of local truth. And maybe that felt very similar to the kind of things we were doing when I was talking about verifiability. So geometric logic is still important. So geometric logic is very important for topology. But there's some differences between geometric logic and intuitionistic logic. Because in geometric logic, like in topology, when you have an open set and you want to take its complement, you don't expect the complement to be another open set. You expect the complement to be a new thing, a closed set. And these correspond to what are called refutable properties. So these are properties that when they fail, you can tell that they fail. So this is something completely new. It's not the same kind of thing, this kind of negation. But in intuitionistic logic, we really wanted everything to be the same kind of thing. So we wanted that when we took negation, we have to take the interior of the complement. And the fact that in geometric logic you get something new in some sense makes it much less expressive, right? Because now you can't, it's difficult to combine the kind of verifiable propositions and the refutable propositions and do things like this. On the other hand, intuitionistic logic is very expressive. And not only can we talk about things like implication, we can also talk about quantifiers, and we can do higher order logic, and we can do pretty much all you can do in normal classical mathematics, we can do in intuitionistic mathematics. But geometric logic is very, very closely aligned to the topology. So that's also very important. Okay, good. Any questions? Okay. So we have just a few more minutes left. I'm wondering how much I want to go into the things. Yeah, so I guess if anyone does have any questions now about what I've done so far, you ask them, and otherwise I will go on a little bit more. Okay.
So
yeah.
Maybe the sweeping statement about how you can sort of do almost everything you can do in classical logic. I mean, I guess what can't you do?
Well,
compactness theorem, what does that mean?
Well, I guess. So yeah. So I get what I mean is like all the logical things that that you can formulate. Maybe not all the theorems are still true. Though I guess many of the theorems do become true, but you just need to formulate them in the point-free way. So there are many things that end up not being true, like constructively, like naively. So people will say things like, the real numbers aren't locally compact constructively and stuff like this, which makes it sound terrible. But the real numbers, the locale of real numbers is locally compact constructively. So if you do things in a point-free way, many of the things that people say fail actually end up working. So hopefully, kind of as we go later in the course, you'll start seeing examples of this. But I think for now, just very quickly, I want to start talking about the lattice of truth values, and we'll continue about this later. So next week. So classically, we just have two truth values. We have false and we have true. Okay, very straightforward. What happens constructively is not so straightforward. So there's still a lattice of truth values. So we can consider the truth values, and we call this set omega. So if you know any topos theory, think about the subobject classifier, but you don't need to know any topos theory to understand this. So why is it a lattice? Well, it's ordered by, like, B is larger than A if A implies B, right? That's kind of the idea. This gives an ordering. And what does A implies B mean? Well, you could say it's a hating algebra, that is. Or you can say that, well, you assume that A is true, and then you try and prove B. So exactly like how we prove A implies B when we write proofs, we usually assume the hypothesis and try and show the conclusion. So this gives an order structure. And then the meets and joins are just given by conjunction and disjunction, as you would expect.
Graham, are you conflating propositions and truth values when you describe this?
Yeah, somewhat, yeah. So I guess I'm conflating all propositions that have the same truth value. Yeah, that's true. You could consider all propositions if you like, and then you can like quotient by ones that imply each other, right? By logical equivalence or something. But yes. So if we have, so again, I'm kind of doing this, but anyway, if we have a element of omega, this is some kind of truth value. So we can say, it turns out you can prove that P is true. It's this largest element. So there is still a largest element and a smallest element of this lattice. So we still have a true and a false. And you can say P is true if and only if P holds. So if and only if P corresponds to a proposition which holds, if you like, Peter. And then on the other hand, we have P is false if not P holds. Okay, makes sense. But now, if we want to say either P is top or P is bottom, that's equivalent to excluded middle, right? That's saying P or not P. So this is not necessarily true. We can't prove this. When I say we can't prove this, it doesn't also mean it's false, right? But it means that it's at least, it might depend on the kind of model you're talking about. Like, so it is true classically, but we can't prove it constructively that this is in fact true. Which is saying it's not the same as just having something which is false and something which is true, right? It's more subtle than that. On the other hand, what we can prove is that if P is not true, then P is false. So I think the term excluded middle is confusing. Excluded middle makes you think there's maybe a third truth value. Sometimes people even call it excluded third. There's some third truth value which is neither true or false. But this tells you that that's not true. It says the moment you know it's not true, it must be false. So it's much more subtle than saying there's a third truth value. It doesn't have exactly two elements, but it's also not true that it has like more than three elements. Okay. So this is a bit confusing. And it might be particularly confusing if you think of that example of local truth, because you're like, in that example, we had a truth value for every region. So what on earth is happening? But you need to understand there's the kind of external perspective where we look at the model from the outside. And there's the internal perspective where we reason with the truth value, with the kind of operations meaning different things. So when you're working inside the model and you have this U, which is like not the entire space, not the empty set, and you say, if this equals true, it's not going to give you an external truth value, yes or no. It's going to give a region on which it's the same as true. And the set U is going to be the same as the entire space on U, and it's not going to be the same outside of U. So that truth value will give you U itself. And then the other one, where P equals empty set, that's not going to be true at U, but it is going to be true on the interior of the complement of U. And then, so we can still see, kind of, if you think about that, when you say if P is not true, then it's false, this will still be true in that case. So even though, like, so I guess my point is you need to kind of reason entirely within this new kind of logic. You shouldn't like take a step outside and say, oh, there should be multiple truth values. As far as the logic's concerned, it's not true that there's an additional truth value. So I hope that's somewhat clear. but we will see more of that next time. I think it's probably time to stop. I will just, though, we will continue next time, but I just want to maybe end with a, why are we bothering? Why should we work constructively? And the idea is, when you prove a result constructively, it's going to hold in much greater generality than the classical results hold. So when you prove it constructively, you will get the classical results, but you can also get other things. So if you know anything about topos theory, you can interpret in different toposes. So here I have examples, but you can just think of these as different universes for doing maths. And you prove the result once, you get the classical result. You get kind of, here we're doing topology. So if you do it in this universe where everything's computable, you get some results of computable analysis. When you do results in a certain sheaf topos, you get results in fiber-wise topology. So you just prove the result once, and then by interpreting different toposes, you immediately get a number of different results. But I'll talk about this maybe in a less rushed way and in more detail next week. Of course, we'll see a worked example quite a lot later. But next week, I will go through the rest of these slides, and we'll move on to some more constructive things. But that's all I have for now. Great. So, any more questions? Any questions from online? Okay.
Yeah. Thank you so much.
Okay, thank you.
I just wanted to ask that you still want your lattice to be distributive. Is
Yes.
there
any... Yes. So yeah. So a hating algebra is always a distributive lattice, because if you have an adjoint, it means that if kind of taking meet with A has a right adjoint, it means taking meet with A preserves join. So that gives you your distributivity. So the lattice is always distributive. Yes.
Yes. But we're not therefore speaking about of logical structures where the lattice is not distributive.
Yeah, I guess if usually in logic, we usually like to assume some kind of distributivity. The logic which would describe a non-distributive thing would be quite strange, much more strange than constructive logic, I guess.
Correct. Yes. Okay. Thank you.
Sure. Yeah, but hopefully some more of these intricacies of constructive mathematics I will be able to talk about next week.
Okay, but seemingly it seems that much of the usual topology can also be done with without the distributiveness.
I don't know. I guess I need to think. I've never thought seriously about how that would work. Yeah, I feel like my feeling is that a lot will break, but I guess I don't know. I've never looked at it, so I'm not sure.
Yes. Many things will break, but many things would not.
Yeah.
For instance, you can define compactness and you can define Hausdorffness and their serious properties.
Yeah, true. I can imagine doing stuff like that. Yeah.
Okay. Okay. Thank you.